Now, we know that those p orbitals are orientated perpendicularly to each other. There's one along the x-axis, one along the y-axis, and one along the z-axis. But if we have orbitals like that overlapping to form sigma bonds, that does not account for the observed tetrahedral shape of the methane molecule. We talked far too much about that last week. But the methane molecule is a tetrahedron. And we don't get that from these orbitals that are at right angles to each other. So there must be something else going on here. This, just looking at overlap of orbitals doesn't explain the observed shape. And so one solution, it's called molecular, well actually it's valence bond theory. We don't need the name. One solution is to combine those 4 atomic orbitals and make hybrid orbitals. So here are the valence atomic orbitals of carbon. There's the 2s orbital, that's going to have 2 electrons in it, and the 2p orbitals, there's 3 of them, and they will each have 1 electron in them. So this would predict that these 2p orbitals could overlap with other things. We would expect carbon to form 2 bonds, and we would expect that the angle might be either 180 or 90 degrees, depending on how you view the orbitals. And neither of those situations is true. So what we're doing here is we're taking these orbitals, 3 p orbitals and 1 s, and we're combining them, we're melting them together, making a hybrid orbital. So now we have 4 orbitals that are equivalent, and we call them sp3 because this is the averaging or combination of 1 s orbital and 3 p orbitals. If we draw those out, it's a mathematical addition of these of the s and p wave functions, and what we get is something that's shaped like this. It looks a lot like a p orbital, except one of the lobes is much larger and one is smaller. And because there are 4 of these and they're equivalent, they're actually going to make a tetrahedron because they're going to arrange themselves symmetrically around the nucleus of the atom. Now in this illustration, we don't show the back lobe of each of these because it gets all cluttered up, but the back lobe is there and it can be significant at times. Any questions? Yes?
So those 2 diagrams are the same thing?
This is showing one of the 4 hybrid orbitals, and this is showing all 4 of them put together.
Okay, so they kind of go into each other?
Yeah, they do. They kind of go into each other. This one has a back lobe that would be coming down right between these other 3. And this has a back lobe that would be sticking out here. Yeah, it just requires some visualization. But this is a great explanation because now we would predict that carbon would form a tetrahedral shape when it makes bonds. And if we look at these hybrid orbitals, they each have 1 electron in them. And so each is going to form 1 bond, carbon's going to form a total of 4 bonds, and it's going to have a tetrahedral shape. And that matches up really nicely with our observations of what happens. So those hybrid orbitals can form sigma bonds. So here's that sp3 hybrid orbital. It can overlap with an s orbital of another atom and form a sigma bond. Or we could have 2 sp3 orbitals overlapping with each other end to end, and that will form a sigma bond also. And this little designation is just telling us what kind of orbitals are overlapping to form that bond. So then when we look at a molecule of methane, here is the carbon atom with its 4 hybrid orbitals, sp3 hybrid orbitals, and these hydrogen atoms, which you can't see very well on this screen. There's actually circles here. So here are the hydrogen atoms with their s orbitals, and as they approach, the s orbital of the hydrogen overlaps with the sp3 orbital of the carbon and forms a sigma bond. And again, you can't really see them very well. Oops, it's down here. But those are the hydrogen atoms. And this gives us the predicted shape of methane, the tetrahedron. Any questions? It was either so clear that nobody has any questions, or it was so awful that you can't even formulate a question. It's one or the other. We'll go with crystal clear. You'll ask me questions later. We've already looked at that slide. We kind of looked at these. I just redid them to reflect better what your book calls them. Your book calls this a 3D structure. This is where we have the dashed wedges, the solid wedges, and the solid lines. And it's important to understand the solid one is coming out at you, the dashed one is behind the page or the screen, and these just normal lines are in the plane. And that's the easiest way to indicate a tetrahedral shape. We've gone over that with the ball and stick model. It's helpful because it helps us to see the bonds. Space filling helps us to see the shape of the molecule better. And each of these is useful for its own purpose.